Hello, hello, can you hear me? Okay, perfect. Hey everyone, I'm here to present Logic-in-Memory Computer by Harold Stone, which was published in IEEE Transactions on Computers in 1970. It is quite an old paper, and I'll start presenting this. So start with an executive summary of the paper and what it tries to, what it actually tells us. So motivation. This is the start of the 1970s, the decade. And there has been a lot of technological advancements that has made it possible to pack in more complicated hardware circuitry to perform more complicated operations. For example, this was when there was starting to be an evolution from medium-scale integration to large-scale integration. And throughout the 1970s, it would evolve further into very large-scale integration, VLSI. So now that we can actually get more complicated circuitry in, where do we actually make it more complicated? What do we target? What do we optimize more? The author identifies memory caches as one place that could benefit from more complicated circuitry. For example, in caches, there's continuous data movement between cache and CPU, which leads to quite a bit of overhead in more latency and also in high energy consumption. And the author identifies this as one location that can be further optimized. The paper mentions that microelectronic memory caches can be enhanced by enabling processing directly in the memory array itself. If we are able to perform basic cache operations directly in place in cache, instead of having to move it from cache to the CPU, this would reduce quite a bit of overhead. And for this, the author proposes a logic-in-memory cache. The author says that we should augment caches with the ability to perform certain operations in memory. These are some basic operations, such as searching through the cache, and, for example, searching over equality or searching over comparison, or performing sector arithmetic, like sector addition, sector multiplication. This reduces the overhead of copying these words from cache into CPU registers and then moving it back into cache. Finally, the author also proposes another means of optimization, which is to provide program control over cache behavior. If the cache is able to take hints from the program and is able to adapt to the way the application is being executed, this could provide further adaptability to the way software works. One possibility is to control the way memory is loaded into cache in either row major order or column major order, for example. And another possibility is to access with bit slice mode. What this means is that only certain bits from each word is loaded into cache. We'll talk about this more later in the course of the presentation. So I'll give you a quick outline of what the rest of the presentation is going to look like. I'll first give a background of how caches work, and then we'll talk about logic in memory, and then we go on to program-controlled caching. Then we give conclusions of the paper, as stated by the author, and then we move on to more my personal analysis of the paper, where I talk about the strengths, the weaknesses, and some key takeaways of the paper. And then finally, I conclude by leaving some open discussion on what can be done next. So caching. We are quite familiar with this, but we'll still go over it a little bit. Caches were proposed by Wilkes in his 1965 paper on Wilkes slave memory. The key idea of caches is to function as a low latency buffer between main memory and CPU. So this is something that it looks like. It's a buffer between main memory and CPU, and it allows us to cache recently accessed memory locations. It's meant to exploit the principle of locality. The principle of locality is when programs access particular memory locations continuously, and most programs do not really touch beyond a certain bound of memory and are more focused towards certain memory locations. For example, when a program operates through an array, it would mostly bound itself to the memory where the array exists. And caches are meant to exploit this in a sense that if we can cache the recent memory accesses, most likely we are going to prevent future accesses directly into main memory. While caches are orders of magnitude smaller than main memory, for example, cache is somewhere between 16 to 64 kilobytes, and main memory is in the order of gigabytes. In practice, 95% of data accesses are still in cache itself. So even though there is a huge size disparity, we are still able to save a majority of accesses to main memory. The key benefit of this idea is that CPU now views memory as having the low latency access times of caches, but with the high capacity of main memory. So in a sense, CPU is really blind to this buffer that exists and just really thinks of main memory as being this really fast access times. An interesting point that you may have noted if you've read the paper is that the idea of using main memory as a buffer for disk actually preceded that of using caches as a buffer for main memory. And you can see that the author, when he provides a background on caches themselves, he likens cache behavior to that of main memory buffering access to disk. Let's talk a bit about what the kind of cache that Stone is actually using. It's mostly similar to what we've looked at, but it's slightly modified. He proposes a cache of 16 sectors, we call them blocks, of 1 kilobyte each. So it's a 16 kilobyte cache. And one sector stores one contiguous memory location of 1 kilobyte or 1024 bytes. So a sector is identified by a starting memory address into main memory, and it stores the entire contiguous location of a kilobyte. And finally, words in cache. So this, words have been modified in cache to include an additional tag bit. So each word would have a tag bit associated with it. What this means, we'll explore a bit deeper into the presentation. So let's move on to logic in memory as proposed by Stone, and what the kind of operations, what the benefit of this is. So as we explored a bit earlier, the main problem is that there's continuous data transfer from cache to CPU. And this leads to a lot of unnecessary transfer overhead and a lot of unnecessary energy use wastage. So the idea is that if we can enable caches to perform these basic operations, we now save the time and energy required to move all this data from cache to CPU and then back into cache. The solution for this is to enhance caches with logic in memory operations. And now cache, in a sense, functions as a basic compute unit. So as we can see, we're already moving away. Even in 1970, we've already started to explore moving away from traditional von Neumann architecture, where CPUs are the central computing unit, and then everything is built around the CPUs, to moving computation into caches. Here's where we use the tag bits. These logic in memory operations proposed by Stone in the paper manipulate these tag bits And the way they manipulate, let's talk about in the upcoming slides. So some key operations proposed by Stone are searching on masked equality or threshold. So you search on a pattern, set the tag bits of all matching patterns, and replace first matching word with the argument. We'll look at an animation of how this works. Sector addition or multiply, add two sectors together or multiply two sectors together. Simple as that. And then Stone further proposes some other operations, such as scaling a sector, in which an entire sector is scaled by a scalar value. Copy tag bit, where simply copy all the tag bits of the words in the sectors. And finally, tag bit and, where you can and the tag bit of multiple sectors. We will restrict our discussion to the first two operations, as these are the operations that are also concentrated on in the paper by Stone. So search and masked equality or threshold, let's look at how this actually works. So this assumes a sector. And each word has an associated, the value itself and the tag bit in the word. So let's say we want to search on equality 42 and replace with 50. This means that the tag bits of all words in the sector that are 42 are set, and the first matching word is replaced with the given argument. So we have a match, we set the tag bit. We have another match, and we set the tag bit again. And then we replace the first match with a 50. And in the end, the sector looks like this. Sector addition, add two sectors and replace the first sector with the result. As simple as that. So we have a sector, we add it, and then we replace the first sector with the result of the addition. Let's look at how we implement these operations actually in cache. For comparison, Stone proposes that we should implement them using associative memory, also called content addressable memory. Content addressable memory is optimized for performing high-speed searching operations into memory itself. We address them using the content of memory. What does this mean? So normally when we address RAM, we query it with a memory address to obtain the contents of that memory address. However, in content addressable memory, you would instead query it with the value itself, and then you would get a result depending on the kind of query you use. So it could be something like an equality operation where you'd get whether the word you queried existed, or it could be like a threshold operation where you'd get a word that's closest to it, or maybe it replies with the word doesn't exist in memory. For more circuit level details, I highly recommend taking a look at these papers. Quite old papers, but quite interesting. Sector addition, this is directly a picture taken from the paper itself. So Stone proposes that we should use one adder for the entire cache instead of using a separate adder circuit for each sector in cache, as this would reduce duplication, and then we could load multiple sectors into this common adder circuit to perform the addition we need. So now let's move on to program-controlled caches and how programs can actually provide hints to caches or control caches using provider operations. The problem is that hardware can't really adapt to the way software works. It cannot take hints from software, or can't really work based on the way each application, or based on the characteristics of each application. So the idea is that we are going to provide mechanisms for software to control the way caches behave and to control the operations that are being performed on caches. Program can control cache using special instructions. Program can provide hints on the memory that it is going to access, and it can also provide hints on memory that it's no longer going to access, so that caches may evict this memory instead of using the default replacement policy. We'll look into this a bit more in detail. Control the order of loading into cache, for example, order of loading matrices. So you may want to load a matrix either in row major order or column major order. Bit slice access mode to load particular bits of words into cache. This means that we can load not the entire word into sectors, but load particular bits of each word into sectors, so that we can now load more words into the same sector. Sounds a bit confusing, I know, but we'll look at how this works in a bit. So the goal is to anticipate requests for data based on program hints. How are we doing this? one useful hint would be that the program can say that it's no longer going to access this memory from cache. So for example, once it's operating on an array, it can provide a hint saying that we are no longer going to touch this array anymore. Then the cache may just evict this array instead of using its default replacement policy. You can also prevent a sector of cache from being evicted if you want a sector in cache to stay, because you're continuously performing operations on that sector, reading from or writing to it, and you don't want it to be evicted when in contention from other processes. Then you can mark the sector as pinned. It's also very recently being called pinning. For example, we have a very simple program that sums over the array. It hints saying that the program needs this array to be brought into cache because we're now going to operate on this array. And then once it's done operating on the array, it sends an instruction saying that this can now be released from cache. Secondly, controlling how matrices are loaded into cache. We may now load rows or columns of matrices into cache depending on the kind of operations you want to perform on them. A key change that this requires is that since at the beginning, we talked about how a sector in cache stores contiguous data location. So it only stores the starting address, and then it stores the entire 1024-byte sector into cache. However, now we need to change the way these words are being addressed to the physical memory, in a sense that these words can now point to regularly spaced addresses instead of continuous addresses. For example, take a simple matrix. Let's assume that this is how it's stored in main memory. And if we are loading it into cache in row major order, then we simply store A and A plus 1. However, if we want to load it in column order, then we store it as A and A plus 2. Why is this really important? For example, let's say you're performing matrix multiplication. Then instead of loading each row and then having to evict them, load them again, you simply load the rows of the first matrix and the columns of the other matrix, and you can directly perform multiplication on them. Finally, bit slice access. So why is this really important? Because let's say we are performing operations on a lot of words, but we're only manipulating certain bits of the word. For example, your word could be a message where the first bit indicates something special, and you only really want to look at the first bit of all of these words. Or maybe you're performing a lower half addition, and you only need the lower half bits of the word. In this case, if you could only bring those specific parts of the word into cache, then you can perform more efficient operations with a smaller amount of cache size. So if you have n bits per word, and you can perform bit size access, you may perform operations on up to n times as many words with the same cache size. So for example, let's say we have an array that looks like this, and we load only bit 0 of each element into the cache sector, and you can see with half the size, we are able to still operate on the entire set of words. Finally, conclusions of the paper. Let's quickly summarize what the paper has talked about and then talk about some key takeaways from the paper. So our problem was that cache to CPU transfer overhead is a significant bottleneck. The author proposed the idea of using logic-in-memory operations to perform operations directly in cache itself. This reduces CPU to cache transfer overhead. Some key takeaways of the paper is that, as we already discussed, and we can see that the resulting architecture of this is quite different from traditional von Neumann architecture. Now, in a sense, we have a basic computing unit in cache itself. And the further we augment this basic computing unit, at one point, it is going to turn into its own full-fledged CPU. The cost versus benefit trade-off of these operations must be investigated. Is it really worth putting this extra complexity into the cache? And is the benefit we receive really worth all this complexity? Utility of the proposed logic-in-memory operations. So we've seen a number of operations, but are these operations really useful? Can these be applied in real-life applications and real-life workloads? And would they help the programmer? And finally, the challenge of providing programmers control over the cache. we've talked about quite a few special cache-specific instructions. However, how do we provide control of these instructions to programmers who work with high-level programming languages, which abstract away a lot of the low-level features? Now let's move on to my analysis of this paper, and let's talk about the strengths of the paper. So this paper is the first documented paper on introducing the mindset of processing in memory. And the paper identifies an important source of overhead that's present in modern computers. The paper also identifies the importance of performing hardware-software co-design. And we've also seen some interesting means of controlling the cache using some special program hints and instructions. This is arguably the main contribution of the paper, which we'll talk about more in the discussion section. But the author has really provided key insights on future challenges. He has discussed a wide range of concepts that have branched off into entire research fields in themselves. And this really touches upon a lot of different fields. And a lot of challenges discussed in this paper are actually being faced by researchers of our time. Also accurately predicted the challenges that will be faced by future compilers, which we'll also look into a bit more in the discussion section. Oh, sorry. Yeah, and also led to further research in processing and cache technology, which is a bit new, I would say, because we've been talking a lot about processing in memory in class, and we have never really seen anything about processing in cache. But there's a lot of very recent processing in cache papers and work that has actually identified that processing in cache can provide some great benefits to specific workloads. The background section where the author talks about caches is quite an interesting read, because it's important to understand that caches were just proposed 5 years before the publication of this paper. And the author really provides a comprehensive explanation of how caches work as buffers to main memory. And finally, it's a very interesting read. If you've read the paper, you can really see that it reads like an essay and it flows really well. It's quite interesting. Finally, some weaknesses of the paper. Why cache? The author talks about enhancing the cache with logic in memory operations, but why does the author concentrate on caches? As we are recently seeing, there's a lot of processing in memory research going on. It could very well be the case that back in 1970, the bottleneck was not in moving data from memory to cache, but it could have very well been that the bottleneck was in moving data from cache to CPU registers. However,
Looks like we lost the presenter. Maybe the laptop is out of battery. Let's wait until they get back to us.
Unfortunately, that's one of the weaknesses of the paper. We don't really know where the bottleneck was, and we don't really know why the author is concentrating on caches. And that's one of the reasons why the author doesn't really tell us what the bottleneck is, where the bottleneck is, and why it's the bottleneck. So yeah, unfortunately, I don't have an answer here.
5 years old at the time. The idea of cache properties. It was proposed in this paper in 1965. Yeah. There was an implementation of the state memory, actually, I think around 1967 or 1968, in the IBM 360/65 computer, I believe. And the author briefly mentions that in the paper. So if you're interested in that, you can also take a look at the background section of the paper, where the author talks and compares it with the implementation in the IEDM. Yeah.
Maybe it's not directly related.
It would be interesting because you said that a great part of the traffic, data traffic between the CPU and the happens between the CPU and the cache.
Yeah.
So it is likely that in more modern devices, it's this traffic happens mainly between the CPU and the L1 cache.
Mm-hmm.
So it's not a factor of the of communication between two different chips, because I've read the paper and there it's mentioned that the cost of a chip could be driven more by the number of pins than by the complexity of the chip.
Yeah.
So maybe the introduction of an on-chip cache that impacted the development early on of this technology.
That is definitely a possibility. Yeah, yeah. It's a bit unfortunate, which I'll also talk about in a little bit, but that the author himself did not really build upon this work or really answer the questions that are left as open questions in this work later on. So we don't really know from the author himself if the work has spawned off into anything else or if anything else was really directly influenced of it. But yeah, that's a great point. I agree. It could. Does that answer your question? Okay. Good question. Got a lot of questions. So one of the questions was, why did this paper, this really introduced processing in memory, the mindset of it, back in 1970. But why did this not gain much traction back then? And I believe one of the reasons might be that the paper was more of a concept paper and did not really propose an evaluation methodology or really concrete numbers on why this would be better. And I had some questions from you as well. Yeah, that was one question as well. And then I believe I had another question from you. Yeah, another question was, what fields did this, and one obvious field that this inspired is processing in memory. What other fields did this inspire? And it's processing in cache, hardware software co-design, and compilers from my analysis, and it could be way more as well. I believe that was it. I have a question from Onur as well. Sorry, could you maybe rephrase what you asked? Yeah, yeah, okay. Yeah, yeah. Onur was, Onur remarked that they don't really talk about memory in this paper. And does the author not talk about memory anywhere? And yes, the author only mentions memory when it comes to talking about cache being a buffer for it. And the author talks about memory when in the background section where he likens cache to being a buffer for main memory in the sense that main memory is a buffer for disk. I believe that's it. All right, let's move on. We were at the weaknesses section, right? Yeah. So we see that operations on bulk data move data continuously from memory to cache. So why does the author focus more on in cache, and why does he not focus on processing in memory? This is not really justified in the paper. No evaluation provided. You're probably wondering why my outline does not contain an evaluation section. That's because unfortunately the paper does not contain one either. The paper does not discuss any potential trade-offs or benefits from these operations or from augmenting cache with processing in cache logic. And he does not even provide a theoretical estimation of possibly how much better it could be. He does acknowledge the need for investigation, but delegates it to future work. And there hasn't been a follow-up work from the author on this paper. So we're kind of left wondering about whether does this actually provide a benefit? Are these operations really useful? Finally, there's no discussion on the searching operations. So the author mentions that we can use associative memory, and he cites some prior work in associative memory, but the paper does not really tell us how this can be repurposed for our use, or how these can be improved upon, for example. Vectorization is not investigated. As we might have seen from the sector adder multiply operations, they seem to be very prone to exploitation by using vectorization operations, and could be greatly improved by using vectorization. However, this is not discussed in the paper. Okay, let's move on to some key takeaways of the paper. This is the first documented paper discussing processing in memory. So it kind of set up a mindset for how computing can really be moved into caches and even further into memory, and this could really provide a benefit. And this has provided a mindset for processing in memory that has later branched off into an entire field. As we can see now, we've spent quite a significant amount of time in the seminar, also in the computer architecture course, in talking about processing in memory and really exploring processing in memory work in detail. It's an interesting and insightful read on the possibilities of the future, and highly encourage everybody reading this paper to really read between the lines. As normally when we're reading a scientific paper, sometimes we get a bit lazy and we only really concentrate on the technical details of it and the evaluation and the conclusions, and we kind of skim over any author commentary in the paper. But this paper, arguably, the most important part of this paper is the commentary provided by the author in between the technical parts, where he makes some really insightful comments on what would be real challenges in the future. Yeah, and these challenges have been faced by researchers of our time. It's also very important to see the paper from a historical context, because it was just 5 years since caches had just been proposed as a scientific idea. So finally, let's get to the discussion part. We'll talk a bit here about what the paper may have inspired the fields, the kind of research that was that's happened and that is still going on, and some open questions for future researchers. Processing in memory, as we've seen, is a new field of research with a lot of highly promising work. The modern primer on processing in memory came out in 2020. It's from its own words. It says that a paradigm shift towards data-centric computing design can greatly push the boundaries of future computing systems. And it has been only 2 years since the publication of this primer, and we are already seeing processing in memory being adopted mainstream into industry. UpMem, Samsung, SK Hynix, and even Alibaba have produced some major PIM modules. We even had a lecture about a discussion on the Alibaba processing in memory module in one of the Safari brainstorming meetings. So a question for the future: will we have PIM chips in our computers in the near future? So in the future, can we have like a module in our computer which has processing in memory capabilities? And can programs exploit this, use this, and can this provide benefit in consumer workloads? Let's talk a bit about processing in cache research. Compute Caches HPCA 2017 proposes in-place computation in caches using very large vector computational units. It proposes some basic operations like XORs, ORs, and ANDs of blocks within caches themselves. And these vector computational units are, in a way, they abstract away the design, and they look, in a sense, like vector units that are kilobytes large as compared to SIMD computational units that are just a few bytes. Neural caches, they describe an in-cache parallel computation possibility to accelerate deep neural networks, and they describe how the pooling and convolutional layers can be computed directly in cache instead of moving into CPU. Finally, duality cache for data parallel acceleration. They propose an in-cache computation architecture for floating point arithmetic and transcendental functions. Transcendental functions are especially interesting because they provide a framework to perform sine, cos, exponent, and logarithmic operations directly in cache itself. Can processing in cache and processing in memory benefit each other? Can we have a system where not only memory is augmented with processing capabilities, but also the cache is augmented with processing capabilities? And can they work together to benefit each other? Hardware software co-design. So one paper in 1986 already talks about how cache misses can be handled in software. Just like how page faults are handled by the operating system, software can also handle cache misses and have a custom handler for what happens when a cache miss occurs. This is tolerating latency through software controlled prefetching in shared memory multiprocessors. Another 1991 paper where they describe prefetching instructions issued directly by software, where programs, by means of special instructions, can issue to cache prefetching instructions time, which is quite different from the prefetching where cache tries to infer the workload, the access workload that's going on, and then tries to infer whether there's a streaming access pattern, whether it can prefetch anything in the future. Finally, run-ahead execution, HPCA 2003, where by pre-processing instructions, well, future program instructions during cache miss cycles, we can identify whether there will be any future cache misses, and these potential cache missing addresses can be fetched in advance. To what extent can hardware software co-design be realized? Recently, we're seeing a lot of research into virtual memory and how virtual memory can work in conjunction with software, and the buffers that are used for this can also really benefit from software hints. How much further can we go with hardware software co-design? Finally, compilers. The paper identifies challenge of providing software access to cache control via high-level programming languages. We come back to duality cache, which we discussed a few slides earlier. The paper is also interesting in the sense that not only do they provide a framework for performing floating point arithmetic in cache, but they also proposed a compiler that can compile CUDA programs to use duality cache instructions. Compiler support for software-based cache partitioning. In this paper, they propose an idea where real-time applications that require real-time servicing and have real-time schedules can partition certain locations of the cache such that these areas in cache cannot be evicted or interfered with by other tasks. And the paper proposes compiler support for these cache partitioning instructions. Finally, a challenge for the future is, can compilers support and optimize special PIM instructions? In recent PIM research, we are seeing a lot of PIM modules that come with specific instructions that can be used to process in memory. Can we create compilers that not only compile to these instructions, but can also accurately identify how these instructions can be used to optimize, and how these instructions can be optimized in different ways, or how they can be intercombined with each other? That's it for my presentation. Thanks for your attention, and we can take any questions that you may have now.
So I think you have some really interesting discussions. So can you maybe go back to the first one?
Yeah.
Processing memory. Will we have chips in our computers in the near future? I think this is a really interesting question. So now in the machine learning age, a lot of these operations are dot products, matrix vector multiplications, which are excellent for crossbar arrays.
Yeah.
And I think so. My hypothesis regarding this question would be yes. This is really interesting for embedded devices, and I'm going to go back to this because I know about a project for. It's about detecting epileptic attacks in people that have epilepsy. A small processing and memory chip which is able to, which consumes very little energy when doing these operations, which is what most of machine learning consists of, matrix multiplications. Which with this type of an idea, processing in memory, is going to consume very little energy, and so can then, for example, be implanted in the brain. Well, not in the brain, but let's say in the skull of a patient with epilepsy. It can stay there for a very long time, and yeah, it does the operations there. So yeah, this isn't really a question. I just thought.
No. Thanks for contributing. Yeah, it's an excellent point, and I think it's very interesting. Feel free to not only ask questions, but also just add on to if you have anything interesting to say about the research.
About the same question, when I read it, I thought, what does our computers mean? Because I mean, it could be personal computers,
yeah,
or also embedded systems, or something, a specialized device that we use.
Yeah.
And I wondered, is it envisioned to be kind of a modular system where you have specialized modules that you can use in your personal computer, or does it mean our computers as a society, like in server clusters or something like that?
By our computers here, I specifically mean our desktop computers. For example, this laptop, the laptop that we use right now, can we have consumer chips? So, but the way you purchase DRAM sticks, could you also purchase a PIM stick and then stick it into your computer and let it work its magic? And would it automatically provide some kind of benefit? For example, in the future, just like how DRAM chips nowadays are plug and play, in a sense, could we have plug and play PIM chips?
Anyone else?
I think Andrew had a question.
Yeah, I guess to continue this discussion, I was wondering, do you know, because there are all these, you mentioned the ones that are currently being created, like the UpMem sticks, the Samsung PIM stuff, SK Hynix and all that stuff. Are those not plug and play? Like do you know the additional work that's needed for those to sort of get up and running?
From my knowledge, from what I've read, they provide specific instructions So you would need programmer knowledge so when you're programming something, you would need to make use of these processing in memory instructions to take advantage of the processing in memory capability provided by these sticks. So if, for example, if processing in memory mindset becomes mainstream in computing, then we could in the future see all programmers requiring to learn processing in memory as a bachelor's first year course.
Right. Yeah. Okay. I see what you mean. Yeah. Then I had another question. This is mostly about the weaknesses you mentioned about the paper. I'm not entirely sure I understood if the very first weakness you mentioned, the why cache. I kind of sort of have a rebuttal question. Why memory? Right.
Yeah.
Like you mentioned, he talks about cache and stuff, but why didn't he explore processing memory? Why wouldn't you? I mean, why would that be more interesting than exploring processing and cache? I mean, do you have maybe an opinion on that? Or?
Yeah, that's a great question, actually. So in recent processing in memory research, the first thing that we always talk about is not really talking about processing in memory, but we, of course, ask the question of why processing in memory. And we see a lot of research where a significant amount of time is being spent simply in data movement. For example, the paper published by Google, where they talk about how a significant amount of compute time and energy is spent simply in moving data around. So why I say that is a weakness in this paper is that the author does not provide some kind of justification or some kind of metric that says, oh, we're spending this much time and energy in moving data from cache to CPU. This is bad.
Okay, yeah, makes a lot of sense. Yeah. But in that sense, do you think that that's, because you're talking about a paper and studies that are done very recently. Do you think that was also the case back in the 70s?
Excellent question. Actually, I don't think so. I think that back in the 70s, it may have been a completely different picture. Maybe back in the 70s, they were really constrained by moving data from cache to CPU. And maybe that really was the major bottleneck. But the paper would have really helped in convincing the reader if they also talked about how that is actually the bottleneck by providing some kind of numbers or metrics.
Okay, yeah, thanks.
Yeah.
And one last thing, sorry for
hogging
the mic while I have it, because then it's going to go on the other side of the room. And yeah, it's just, do you think that this was meant specific, like this idea was meant for sort of a consumer level? Well, then again, this is the 70s, so consumer level didn't really mean much, or more specifically for like supercomputers, because there's one point, the why didn't he look into vectorization? Yeah. I mean, in the 70s, vectorization was sort of exclusively used in supercomputers, right? Because it didn't exist before, like, what, 66 or something? Mm-hmm. So, I mean, do you think that this was meant specifically for supercomputers and, like, really, they didn't really care about the price, or?
Yeah. No, I don't think so, actually. I think they really do care about the price, because the author also talks in the paper about how, if I go back to the executive summary at the very beginning, this might take a bit of time. Technological advancements have made it economically feasible to increase hardware complexity. So one of the main reasons, the motivation for why the author is exploring improving cache performance is because it is now economically feasible to, since in the 70s, I think in 1970, it was at the time where they were evolving to large scale integration. So it was possible to pack more into the same amount of same microelectronic area. So it was also possible economically to do that. So I think the author really was talking about maybe not consumer level, because at that time, consumer level didn't really mean much, but I wouldn't say that the author was talking about doing it for supercomputers, but I would say it was a general idea for computers.
Okay, so what did you mean then by vectorization?
Yeah, great question. So vectorization actually was first proposed I believe in 1967. So the author could have definitely explored, at least on a conceptual level, of how he could use vectorization or SIMD instructions to vectorize this addition, for example. This is very susceptible to vectorization because they are independent computations. And if you feed them to a vector unit, that would give you quite a bit of performance gain. However, the author doesn't really talk about this, considering that at that time, vectorization was already proposed and was an idea. Yeah.
Hi, so I apologize. I missed the beginning of your presentation, but
Yeah, no worries.
so sorry if this was already covered. But so currently mostly caches consist of multi-level caches.
Mhm.
So does the author propose to essentially do it in the highest level caches or in the lowest level caches? And if so,
Sorry.
I see that basically this could generate quite a potential big problem, which might not have been the case in the 1970s, where you had usually only one core. Currently, when you have multiple cores, you have to take into account cache coherency,
Yep.
and this seems like it could be a potential big problem, and it is a sort of positive point for processing in memory, where you don't have to care about cache coherency issues.
Yeah. That's a great question, actually. And actually, you also kind of provided a partial answer to it. Papers before roughly around 1990 or 1995 in architecture and systems literature almost exclusively talk about single core systems. So it could definitely have been the case that they simply did not consider having multiple cores. But also, I believe that the problem of cache coherency here could be solved using any cache coherence protocol that solves cache coherency for non-logic in memory enhanced cache. Does that answer your question?
Yes. Yeah.
Thanks. Any other questions?
Yeah, you had one slide about processing in cache.
Yeah.
And that made me think at the moment, doing processing in memory still seems pretty new, but if we have processing in cache and processing in memory in several levels, we kind of have to figure out what processing part is done on which hierarchy level, right? Do you have any thoughts about that?
That's a great question. I think that's also something we need to do some future research about. And I believe that one way to start about this is looking at where does data movement happen a lot? For example, with bulk data, when it comes to gigabytes large database tables, for example. In that case, I believe processing in memory would help more, because if you performed those operations in cache, then you still need to move these gigabytes large data back and forth from cache and back. But however, if you are performing, say, mathematical computing where you only deal with a few kilobytes of data, then in that case, it might be better to do processing in cache itself, because then if the data you're working on is a few kilobytes large, you can already bring that into cache, and maybe with a few movements from memory to cache, you can do it. But however, then you'd be moving all that data from cache into CPU registers and back when performing, for example, floating point arithmetic on them. And in that case, I believe processing in cache would help more than processing in memory.
Yeah, I also thought one criterion could be if or how many processing parts are performed on the same bit of data. If it's just one step, maybe you could do it in memory, but if you use it a lot, then it's worth transporting it to higher levels.
Yeah, absolutely.
Right?
That's also a good point.
Anyone else?
Exactly.
Yeah, so another sort of point that might have been already mentioned. So currently caches account for a huge part of the die size. And I can assume that essentially adding this feature to cache will just make it even larger. And as we see the trend for manufacturers increasing the cache size more and more and more, I feel like this could be sort of detrimental to this trend.
Yeah. That's a great point. Actually, that's, again, going back to our weaknesses, in that we don't really have a justification of whether no evaluation, so we don't really know whether this works. And exactly, is it really worth increasing the complexity of cache? And is this increased complexity really going to provide any benefit to any real workloads or applications? Yeah, but that's definitely something that must have been investigated, and the author doesn't really follow it up with any future work.
So the author doesn't have any kind of even like back of the envelope calculations?
No, nothing theoretical either. It's mostly an idea paper, sort of. So there a lot of ideas are proposed, but there's no theoretical evaluation either.
All right, thanks.
Any more questions?
More data movement?
Yeah, there's one here. But maybe you have questions on Zoom or YouTube.
we have
Yeah, we have.
YouTube, but first.
Okay.
So to go back to another thing that the author may not have mentioned, I think it was one of the weaknesses. As for the content addressable memory,
Yeah.
Yeah, I was just wondering, could you maybe expand on that a little bit? Because it was mentioned that it's optimized for high speed.
Yeah.
And I can see that this is, again, basically one example of matrix vector multiplication.
Yeah.
But just any thoughts you have on that? Why was that mentioned exactly?
So because if you were going to perform searching, and if you had, let's say, memory that was highly optimized to query based on data you provide. So for example, you want to identify if 42 exists in your memory array. With regular RAM, with non-content addressable memory, you would be stuck with searching through your memory, through every single address, every single word, checking if the word you want exists. If, however, you had a specific circuit, or however it's called, that is really optimized towards figuring out whether a given word exists in memory, then that would definitely help with performing these operations much faster, right? Does that make sense?
Absolutely, yeah. And this is probably just me not being informed enough. Is this done in any modern systems or content addressable memory? Or
I
is it
believe
rather
content
research
addressable memory
topic?
is used in databases. I'm not really sure about that, but yeah, I think it is used a lot in specific specific systems, like for example in databases, where you might want to give me all the rows in this database that all have city Zurich, for example.
Nice.
Does that make sense?
Yeah,
Perfect.
absolutely.
Any more questions here, or shall we move on to YouTube?
I mean, just to add to that, the content addressable memories are actually commonly used in routers, high-speed routers. And
Yeah.
Prefix matching of a destination address, for example.
Yeah, that makes sense
Very
actually.
useful for that purpose. And there are
Thanks.
also other specialized content addressable memories all over a general purpose processor, right? When you do tag matching, for example, when you do auto order execution. So
That makes sense.
heavily, but scaling up to a very large memory size is very difficult with content addressability. That's the difficulty.
I see.
Because it requires a lot of comparison logic, unless you do it in some really special way.
Yeah. Thanks for the point. It makes sense. Any more questions here?
Can you hear me?
Yeah.
So I was also thinking about the possible weakness of the paper would be the lack of implementation details or difficulties. For example, how the different latencies of the operations would be handled by the CPU.
Yeah.
So for example, the row or versus column load in a matrix would have very different latencies or execution times. So I don't think there was a mention of how it would handle this.
Yeah, absolutely. That's a great point. There is no mention of how this would, what kind of benefit this would provide and how this is handled by the memory itself. So we don't really know. Again, we don't even have a theoretical estimation by the author on how this would work. So we don't really know if this is a benefit and what the trade-offs are, basically.
Yeah, I think we have two questions in the YouTube. So the first question goes like, so the application that you're talking about here, the LogicinMemory in general. So
yeah.
The question goes like, does it have a potential application in the cloud platform? For example, with the help of CXL or CCIX. I think these are like some cloud applications.
I am unfortunately not aware of those cloud applications.
Yeah, but the question in general is like, do you see that this technology would be useful for the cloud platforms in general, let's say?
Yeah, absolutely. Since let's maybe go over here. So if you have a cloud platform basically functions in a sense as a computer, right? So if you have a cache that is augmented by logic in memory, then this would provide better, for example, let's say it's a platform that works with handling deep neural network computations, then you could use the neural cache architecture to augment these computations, for example. But yes, I can definitely imagine it having great benefits in the cloud.
So maybe to intercept that, I mean, I don't want to extend this discussion even more, but those CXL and CCIX are recent protocols, communication protocols. For example, they're different from the DDR protocols. The idea is to have a protocol that enables you to communicate with some, let's say, accelerator or processing in memory engine.
Yep.
And that protocol already has coherence mechanisms built into it.
Okay.
Whereas existing DDR protocol, for example, doesn't have any of that, or PCIe doesn't have any coherence protocol. And these protocols are being developed by industry. Intel, for example, and its Sapphire Rapids release is going to release the CXL version 1, I think. And those protocols can certainly enable or ease the adoption of some acceleration on the memory side also, right? If you attach. Actually, Samsung announced they will produce CXL DRAM as well, compatible with this protocol.
I see.
That can enable adoption of processing in memory much more easily.
That sounds interesting. Yeah, it makes sense. It would take away the burden of handling coherence.
Exactly. Yeah.
You had another question on YouTube, right?
No, I think the second question you have already answered. So the second question was like, what's the scope of application is like how the scope of application is different from processing in cache and processing.
Okay.
Memory. So I think we have.
Yeah. Okay. Great. Yeah. If that's all the questions, then thank you very much for listening to my presentation. Oops. Thanks for listening to my presentation. Thanks to my mentors for their useful and timely feedback. I really changed my slides around a lot because of them. So I got some really well-polished slides. And thanks to Nastara and Safari for making her template available, because as you may have noticed, it's pretty much her presentation template. So, right? Thank you very much.
Thanks, Shashank. While the next person's setting up, I'll probably make some comments. That way we can, or people, if they need to go out, they can go out and get a bio break or whatever they want to. But this, thanks for being the first person to present also. You're the guinea pig, let's say, who was the first to present. But I think this was a very good discussion. It took a bit longer than expected and we had technical problems, but it'd be good to keep the discussion like this going in the future. I hope it's useful for people. And if you cannot attend for some reason, feel free not to attend. I just want to make a comment on caches versus memory, because if you look at this paper, 1960s, right? Late 1960s. At that time, caches are not that different from today's memory, I would say. They're off chip, they're on a separate chip. They're still not large, but memory is also not that large, and applications are not as data intensive as today. So if you think about it, caches are the obvious choice of where you would implement logic. And maybe the author didn't think about the extensions, but maybe he also felt that they were obvious, right? If you put it in caches, it's in some other chip, put it in some other chip also, right? Why not? That's exactly, yeah, exactly. And the work was done actually in 1960s and published in 1970, but that doesn't mean that it was done in 1970. So that's one thought I would put forward. And the second thing is, I think this is a very forward-looking paper, clearly, right? It was written late 1960s. We're going to look at a paper from 2021 that's still talking about processing in memory. But of course, there were good reasons for not adopting it, because things were scaling really well, perhaps, and we didn't have the data bottleneck. I mean, everything we discussed in the memory-centric computing lectures, but this lecture hopefully will gives you a history. Maybe I will correct one thing in the record also. Actually, the first cache paper was not Morris Wilks' paper. That's the most popular paper, but there's a 1962 paper by Cohen, Porter, and Bloom, I think. Cohen, Porter, and Bloom, that introduces hardware caches. It's a bit less visible, but caches are an older idea than 1965. But yes, you were correct that the first real cache was implemented in IBM 360. Wait a second. I think IBM 36085 or 37085, sorry. And it was in 1968. So it was 2 years before this paper. Yeah, and they have a beautiful paper on that as well. Okay. Okay, we should move on.
Okay, can you hear me? Yeah, I think so. Okay, yeah, I just want to very briefly introduce Yannick and the paper that he's going to present today. Yannick is a fourth-year computer science student, and the paper he's going to present, SISA, it's recently published in Micro 2021. And I think it's a very interesting work due to the applications that it's targeting, the algorithms that it's targeting, and also because it's probably, if not the first one of the first works on processing in memory that combine the two main trends, processing near memory and processing using memory. So Yannick, when you're ready.
Okay, so can you hear me? Yes, perfect. So today I will introduce you to a novel programming paradigm to target graph mining. I will also introduce you to SISA, a set-centric ISA extension. And I will introduce you, as Juan said, to an application of PIM, both processing using memory and processing near memory. Well, clearly, I'm not going to present three completely different things. No, I will design a nice co-design across the complete hierarchy. And I will present SISA, a set-centric instruction set architecture for graph mining on processing in memory systems. SISA starts with the problem of graph mining. It provides set-centric algorithms. It also provides a thin software layer for the SISA instructions. Then the software hardware interface is the set-centric ISA extension, SISA itself. And beneath there's processing in memory, using memory and processing near memory to implement that. So we are really taking the expanded view of computer architecture today. To make this even a little clearer, let's start with the executive summary. The problem we tackle are graph mining algorithms. And the motivation of the paper is that those algorithms are bottlenecked by memory and provide non-straightforward parallelism. The goal is to provide a new paradigm that enables high-performance graph mining algorithms. And the paradigm should be applicable to many different graph mining problems. And it should exploit the capabilities of heterogeneous hardware to accelerate those algorithms. The paper introduces SISA, which combines a set-centric ISA extension with processing in memory to tackle the memory bottleneck. And last but not least, SISA, the paper finds out that SISA provides a significant speed up compared to current state of the art. So let's focus a little more on the problem we are facing, because this is crucial to understand. Graph mining is about solving complex problems over graph datasets. There are a lot of example problems. For example, maximal click listing, where you want to find the biggest fully connected subgraph within a graph, or frequent subgraph mining, where you want to find those subgraphs that occur frequently in a graph. And also the application space is very wide. Well, we use graph mining whenever there are graphs. So for example, in bioinformatics, web graph analysis, cybersecurity, and there are many more applications. What exactly are the challenges of graph mining? To make this clear, I've brought these two algorithms. The first one is PageRank, or a very simple version of PageRank that is used by Google today to determine how important a web page is. And the second one is Braun-Kerbusch for maximal click listing. And the difference between those two algorithms is in the marked lines. While PageRank just sends a few messages between nodes and does very basic computations, Braun-Kerbusch has this recursive call and spans complex intermediate data structures. And today we want to focus on those kind of graph mining algorithms because they're bottlenecked by memory. Well, to be fair, PageRank is also bottlenecked by memory, but in a different way. They are often NP hard or have runtime at least quadratic. And as mentioned, they have a deeply recursive algorithm structure and span complex intermediary data structures. So the goal is to provide a solution to enable high performance graph mining, which is the fast execution of such algorithms. It should be applicable to many algorithms. Should exploit the hardware features to accelerate the operations. And last but not least, it should be theoretically efficient. Why? Well, if we accelerate but introduce a lot of overhead, then we've gained nothing. The approach of the paper is SISA, which contains of two parts. Firstly, set algebra. What does this mean? We start with set-centric formulations of algorithms. Maybe a quick introduction to set algebra. I've provided those two vertices, and the neighborhood of each vertex is the set of vertices that are connected to the vertex. So we've got those sets as our basic building blocks in set algebra, and then we've got set operations that work on sets. For example, introduction that contains the intersection of two sets are just those elements that are in both sets. Once we've got the set-centric algorithms, SISA provides an IS8 extension to execute the algorithms. It also provides set representations and fast set algorithms. And yeah, that's on the set algebra side. And the second part of SISA is processing in memory. And this is the overview about this. We've got a control unit that schedules the instructions. And we've got processing using memory and processing near memory to execute instructions. Okay, so let's dig deeper into this and start with set-centric paradigm and set-centric formulations of algorithms. The goal is to take the current hand-optimized graph mining algorithms and restructure them such that they're a composition of set algebra building blocks. How is this done? Well, in our algorithmic formulations, we just use the standard set notion. Beneath that, we have some software abstractions. For example, set iterators or wrappers for the sets. And one layer deeper, we've got the hardware instructions, which roughly correspond to the software instructions. To show you how a set-centric formulation of an algorithm is derived, I've brought this example in which the 4 clicks in a graph are counted. A 4 click are 4 vertices that are all pairwise connected. Let us start with the non-set-centric code. How does it work? Once we are in the inner loop, we know that all the red edges do exist. So in the inner loop, we just need to check whether the blue edges do exist. And if so, well, then we found a 4 click and can increase the numbers of 4 clicks found by 1. How does the set-centric code work in comparison? Well, here we start by choosing 2 vertices, V1 and V2 in this case, and then we intersect their neighborhood. Then we know for those vertices in that set and that they are both connected to V1 and V2. So if we then pick a vertex in that set and choose the neighborhood of this set and as intersected with S1, well, then we found all the 4 clicks for V1 and V2 and the selected vertex V3 and can increase the counter the number of found 4 clicks by the cardinality of the intersection. In this case, it's only V4. And once we've got the set-centric formulation, then we only need to translate that into SISA instructions and got our set-centric code for SISA. So now the question is, why do we do it? What are the benefits of the set-centric code? Well, firstly, it is applicable to many graph mining algorithms. Secondly, the set notion provides simplicity. By reformulating and restructuring the code into sets, many of the non-straightforward parallelism is free and can then be used. And last but not least, performance is also achieved by choosing efficient set operation variants. Okay, so once we've got the set-centric paradigm and the set-centric formulations of code, how are our basic building blocks, how are the sets represented in SISA? Well, there are two ways to store a set in SISA. Firstly, as a sparse array, using just storing the vertex IDs of S, where S is a set of vertices, or as a dense bit vector, where the eth bit set just indicates that the vertex with ID E is in the set. This is maybe a little clearer with an example. Here we've got a graph with the vertices 0 to 15 and a sample set with vertices 5, 6, 7, 11, and 12. The sparse array, well, it just stores the integers 5, 6, 7, 11, and 12, while the dense bit vectors, in the dense bit vector, bits 5, 6, 7, 11, and 12 are set to indicate those vertices are in the set, and all the zeros means those vertices are not in the set. Using both representations, how is a graph represented? Yeah, well, it uses both sparse arrays and dense bit vectors. Why? Well, generally, instructions on the dense bit vectors, as we will see, are faster. But the problem is that they provide some overhead because they are dense. They save zero information. So at some point, it gets more efficient to just save a few integers if the set is very sparse. So now we've got the representation of sets. The other part of set algebra are the operations on sets. And as we are set-centric, they need to be very fast. And SISA exactly provides those efficient implementations of set operations. I cannot explain every set operation here. I'll do it on intersection. Again, the definition of intersection for two sets, A and B, intersections are those elements that are in both sets. So in this case, only the one vertex. And how does SISA achieve performance here? Well, remember that the two sets can be stored in different combinations. And depending on the combination they're stored in, we use a different implementation. If they're both stored as sparse arrays with similar size, well, then we just iterate through the elements and check if it is in both sets. If so, we put it into the intersection. If the size varies a lot, then we can iterate over the smaller set, binary search for the element where we assume it is sorted, a binary search for the element in the bigger set, thus achieving better asymptotic complexity. It gets even better when one set is stored as a dense bit vector, because then we just need to iterate over one of the sets and can check whether the corresponding bit in the other sets are set. And last but not least, the best case, if we've got the sets stored in two dense bit vectors, then we can just take the bitwise AND, and this is the intersection of two sets. But this is not the only choice SISA does to make instructions fast. Whenever a sparse array is involved, then SISA uses processing near memory and uses the high bandwidth of processing near memory to tackle the bottleneck of memory. And whenever only dense bit vectors are involved, we can even do it processing using memory and be even faster. Yes, and as said, there are similar implementations for other set operations like union, difference of two sets, and so on. So now we've got sets. We've got the set-centric algorithms. We've got high-performance set operations. How do we implement them in hardware? SISA proposes the following. Firstly, we have a SISA control unit that uses metadata of the SISA sets to choose the most efficient instruction variant. I just introduced you to the variants of intersection, for example. The SISA control unit decides, okay, we've got this combination, so we take this execution, and as only dense bit vectors are involved, we can process it using memory. But then on the other hand, of course, we have processing using memory and processing near memory to actually implement the instructions. The key contribution here is the interplay of processing using memory and processing near memory to accelerate the instructions, and the SISA control unit that automatically chooses the best operation variant. But I will now dig a little deeper on both variants of processing the instructions. Firstly, how are the instructions processed using memory? As said, we can only do that on sets that are stored as dense bit vectors. And in this case, the paper says we can do it with Ambit and row clone, but also states that SISA is generic. It can be done with other hardware implementations. But as the paper does so, I will now quickly explain how we can do it with row clone and Ambit. We've already got this in the lecture. Remember that Ambit can do in-memory computations, but the operands need to be in certain rows. So firstly, we use row clone to copy the operands into those rows. How does row clone work? Well, if we need to copy within a subarray, we just use the row buffer to do so. If we need to copy between two subarrays or between different banks, then we use the fact that the internal bus is shared, set the destination to write mode, the source to write mode, the destination to read mode, well, and then the data is transferred within the DRAM chip. Once we've got our operands where we want them, we can use Ambit for the bitwise computation. How does it work? Well, if our operands are at A and B, depending on how we charge C, when we activate all the lines, using the equation below, we can either do bitwise or bitwise AND. And once we've got the result, well, then we use row clone to copy it to the destination. So how does processing near memory work? Well, here we use the high bandwidth provided by the closeness to memory. And I've brought, for example, this 3D stacked memory. We've got several memory layers, and beneath the logic layers, and they're connected via very high bandwidth. And again, the paper doesn't state how you should do it. It could be, for example, implemented using UpMem, which is a 2D stack technology, or Tessec, which is such a 3D stack. Okay, that's everything you need to know about how SISA works. We've got set-centric formulations. We can represent the sets in SISA. We have high-performance set operations. And well, then we execute it using processing using memory and processing near memory. Now the paper, of course, also provides analysis and evaluation. And this actually is threefold. Firstly, there's some theoretical analysis, then some analysis about the expressiveness of SISA, and last but not least, some evaluation about the performance. Let us start with the theoretical analysis. Let us remember that SISA demanded that we should not introduce too much overhead, which means the algorithms should be asymptotically optimal compared to hand-tuned graph mining algorithms. And as this table shows, this is the case. Here we've got the different SISA operation variants for intersection. We've got some sample problems, and we see that which is marked by the star, that for each problem, there's one operation variant that actually achieves optimal asymptotic complexity compared to the hand-tuned algorithms. Now the expressiveness, well, SISA wouldn't be a great accelerator if we could only accelerate one problem, and luckily this is not the case. Here we've got several programming models that are compared. We've also got some sample problems, and then the table shows the level of support each programming model provides for the sample problem. And as you can see, SISA is the only model that provides support for all complex problems. So last but not least, the performance evaluation. What's the methodology? We use two baselines. Firstly, we compare SISA to non-set algorithms. and secondly, to set-based formulation of the algorithms. The platforms used are for SISA, we set a platform to match tesseract and ambit, and for non-set and set-based pipeline, set-based baseline, we use a high-performance out-of-order many-core CPU. And also for non-set and set-based, we use bandwidth scalability that is provided by tesseract to ensure fair comparison. The inputs are several graph mining problems like clustering, k-clicks, maximal clicks, subgraph isomorphism, and the data sets are graphs from different areas, thus having different properties, which is important because the performance of SISA and compared to the other models depends on the properties of the graph. So now I've brought you some sample results. The graph mining algorithms here are clustering, then listing 5 clicks, and maximal click listing. They are applied to several input graphs. We use a runtime cutoff to make it more readable. And yes, last but not least, the graphic provides the speed up of SISA compared to the non-set variant, which is the algorithmic and architectural speed up, and the speed up of SISA compared to set-based, which is only the architectural speed up. And what can we see? Well, clustering, for example, is a simpler problem. And for less complex algorithms, the hand optimization outperforms the set-based algorithm, but SISA still provides some speed up. While for more complex problem, already writing the algorithms in a set-based way provides speed up, and SISA pushes this even further. Another important note here is that when we compare the performance of SISA versus the solely set-based algorithms, the properties of the input graph are important. Why? Because SISA is especially good when we can use processing using memory, because it's even faster than processing near memory. So if we have a very dense graph, then SISA will be way better. And in very, very sparse graphs, in the worst case, the set-based algorithm on the out-of-order CPU is even faster than SISA, but that's only in the case in very few cases. So to make a loop, the key ideas and takeaways, we tackled graph mining. Well, actually the challenges of graph mining, because graph mining is bottlenecked by memory and provided non-straightforward parallelism. Our goal was to provide a new paradigm, which we've done by using those set-centric formulations. And what should I do? Okay. To enable the high-performance graph mining algorithms, we found out that it was applicable to many different algorithms, and it exploited the hardware features of processing using memory and processing near memory. We used SISA, the set-centric ISA extension, in combination with processing in memory, and we actually achieved significant speed up. So this is what I've got about the paper. Do you have any questions? Yes.
Set architecture immediately, or I will
okay.
So we don't have to do So my question was, are this set-centric operation immediately more efficient than normal operation, or we have to analyze maybe a graph that has some dimension in order for it to be effective?
It doesn't depend on the graph, but on the algorithm we tackle. If the algorithm is rather simple, then the hand-tuned algorithms, non-set version, are better. While when the algorithm structure is more complex, then using those set-based formulations, we reveal some of the hidden parallelism, and we get more performance that way. Do you understand it?
Yeah, okay, thanks.
Yes.
So I have a question about the set difference operation.
Mhm.
It was in one of the slides. Could you maybe go back to the slide where you show that?
The intersection.
Yeah. Yeah. So
here
in this
it
one,
is.
yeah.
Okay.
So in the step where they search for elements of smaller set in the larger set,
Yes.
do you know how exactly this is done? For example, it's possible to do this in minimum of set A and set B time if we use some kind of hash table based structures. But is that also done here the same way, or is it compared pairwise?
Well, it uses binary search in the bigger set.
Okay.
The assumption is that the bigger set is, or the sets are sorted, and then we can just binary search.
Okay. And the sorting of sets, does that happen as well?
What do you mean?
Is that done manually, or does the algorithm assume that the sets are sorted?
It happens automatically. In the beginning, when you start the program, the graph is stored automatically as using the bit vectors and the sparse arrays. Yes.
Okay. And since this adds an extra logarithmic factor, so it's going to be worst case logarithmic of n log n time instead of n time, does this really affect? Is there anything in the paper about if this could be potentially slower than using, for example, a hash table based search?
No, the paper doesn't state anything about it. It just states that it works that way.
Okay, all right, thanks.
And then there's the next question.
Hi. So I assume the user or the programmer is going to be deciding which way the sets are stored. Is that correct? Whether they're in this sparse or this dense.
Well, I said there is a certain trade-off point when it makes most. Well, usually the dense bit vector way provides the fast operations, but if it's too sparse, then the overhead is too big. And there is a parameter the user can set. Yeah, and then depending on the sparsity and depending on the parameter, it is decided whether it is stored as a dense bit vector or as a sparse array.
So it's not the programmer who decides, it's the...
This.
Okay.
Well, not for every single set. You set just a parameter in the beginning, and then it is done
automatically whether it's going to be okay. And in that sense, so does the SISA controller then basically just analyze the type of storage of the set, right? And then whether it is big or small, and then decides one of those.
Yes, exactly.
This is then done automatically.
Yeah, you have some metadata associated with each set, and the SISA control unit then does it automatically. Yes.
All right, great, thanks.
I have you hear me?
Yes.
I have a question. Is the SISA controller implemented in hardware or software then?
The paper proposes to implement it in hardware to make it as fast as possible.
Okay, but then you have really a full stack altering with ISO, as ISO. So you have the hardware interface, software, and hardware changes.
Yes, exactly.
Okay.
We have also a question on YouTube.
Okay, I can't see
so
it.
it's from Jan. Would it be possible to use SISA for non-graph applications, but also set-heavy workload? Is there some mention of non-graph set-based workloads?
Yes, I think that is possible, but I will talk about that later in the strengths and weaknesses and also in the discussion. So wait until then.
Yeah, great, thanks.
Yes.
So my question will be related to this. I think it was the second step, I'm not sure anymore, just transforming a problem into a set-centric formula. Maybe I'm overestimating this. I didn't study computer science, but this seems kind of complex to me. Is this done by the user, or is this something done by the compiler?
No, the programmer has to do the work.
Okay, right.
Yeah, and I think it's not that straightforward, and there's like the paper doesn't propose to do it exactly this way, then you get the result. So you need to be creative to transfer them into set operations. Okay. Then another question.
So I'm not that familiar with set algebra, but is there no kind of like a programming language specifically designed for sets? And do they maybe have some kind of compiler for this? Or does the paper mention this at all?
I don't know whether there exists a programming language.
So it's programmed.
It's not stated in the paper. I mean, you at some point there's space for future work. You could do it using a compiler, of course, but the paper proposes that that the programmer has to do it.
I mean, here it was suggested SQL, so maybe some kind of a compiler, but that's beyond.
Okay. So if that's it with the questions, I will start with my analysis of the paper. Firstly, with the strengths. I think that it's a very promising cross-layer design. The paper is motivated by the challenges of a problem and then develops a very nice whole stack design around it. What's even nicer, in my opinion, is that we don't focus too much on the problem, but rather on the challenges of the problem. And that way, any problem with similar challenges could be put on top of the stack, and then we have an accelerator for that too. So I would call this a challenge-centric rather than a problem-centric design. Secondly, it is one of the, if not even the first paper that uses the combination of processing using memory and processing near memory. In earlier lectures, we've already seen that each processing using memory and processing near memory provides some performance improvements. And it seems like the synergy of both of them could provide even bigger improvements. In combination with the automatic selection of processing using memory and processing near memory by the SISA control unit, I think this is a very interesting concept to tackle memory bottlenecks in general. Then, what's very nice is there's very few special purpose hardware necessary. In fact, we only need the SISA control unit, which is really, really specific. If we assume that processing using memory and processing near memory are available building blocks, and the SISA control unit just implements very basic logic, so it's very cheap to edit. And last but not least, SISA is orthogonal to other graph mining accelerators. Why is that nice? Well, I think in general, if we've got a problem, it's often in a way, the solutions are often in a way that we've got solution A and solution B, and then one is faster, or maybe they're even both as good on the same level, but they can't be used together. It's different with SISA. For example, you could put software accelerators for graph mining on top of it. There are also some other hardware accelerators that are still bottlenecked by memory. So you could you could add SISA to accelerate it further. So I think it's very nice that SISA can be used as just another building block to accelerate graph mining. But of course, there are also some weaknesses. And the first one, well, you might be surprised to see a strength on the weakness side. But I think the challenge-centric design, or the fact that we focus on just two big challenges of graph mining is also a disadvantage. Why? Well, because graph mining provides some further optimization potential. To make this clear, I've brought this figure. Graph mining algorithms often form such trees, and there is further optimization potential than just formulating it using set instruction. Firstly, on software side, you can detect some patterns in the tree and then prune the tree. The problem is that the tree gets very, very big. So if you can cut off subtrees, actually the potential for improvement is very big. And also on hardware level, there is more parallelism that can be detected. For example, each of the subtrees can be executed in parallel. Sub-branches of subtrees can be executed in parallel. There's also set instructions could be split further and then be executed in parallel. So there's much more parallelism. And I think SISA doesn't dig deep enough into the problem of graph mining. There would be further potential. If we say, okay, well, but the nice thing then is if we've got this challenge-centric design, there are other problems we can put on top of it. Then, in my opinion, SISA is not aggressive enough about this, because the way SISA is introduced, it solves the challenges of graph mining. So I'm sure there are different problems that have the same challenges. Why don't properly propagate this and be a little more aggressive about this? There's just one sentence in the paper that states, yeah, other problems could be put on top of the stack. I think the concept is stronger than just mention it in one sentence. Another weakness is that the performance of SISA compared to the other baselines depends on the input graphs. Well, if we have an accelerator for a problem, it's not that nice that there exist input graphs where the hand-optimized algorithms are faster than the SISA, than executing it on SISA, just because the input graph has some properties that do not fit SISA. And last but not least, I stated this here. I know it is controversial because actually I think a lot of progress in science is done using innovation. However, I want to introduce some controversy. SISA is innovative rather than explorative. It forms this nice cross-stack design, but all the parts are not new themselves. Yes, so let's conclude with some discussion points, some open questions. Remember this strength. Very few special purpose hardware is necessary. In fact, only the SISA control unit, assuming that processing near memory and processing using memory are available building blocks. The question regarding these topics are, is SISA limited to being implemented on processing using memory and processing near memory as the paper proposes? If not, what other hardware solutions could be adapted at the back end of SISA? And could you implement the functions of the SISA control unit in software? Because then, again, assuming processing using memory and processing near memory are building blocks, we wouldn't need any special purpose hardware at all. Then another discussion point. I focused a lot on the fact that SISA tackles the challenges of graph mining, and maybe other problems could be put on top of that. I want to phrase this as an open question too. What other problems could be accelerated by SISA? I think this is not an easy question. I spent quite some time searching for such a problem. And I found one, and I want to show you the mapping to give you an idea how it could be done. And I remembered the lecture about DNA read mapping, and I want to show you how the Grim filter, which we used there, could be implemented with SISA. So remember, we in DNI read mapping, we get a lot of input sequences which need to be mapped to a reference genome. For each read we get, there's some candidate locations in the reference genome. And the problem is that many of the candidate regions, locations have high dissimilarity with the given read. So, and the problem is we have a very expensive check to do so. So the idea is to use a filter and filter out the most incorrect mappings, preserving all the correct mappings, and do that quick. Why? Because then we need to do the checks for the expensive check for fewer locations. How is this done? Using the GRIM filter. In the reference genome, we've got those bins. Each bin is then represented by a bit vector that holds the occurrence of those tokens here in the bin. And then if we get the input read sequence, the tokens that occur in the read sequence are compared to the occurrences in the bin, in the bit vector. And if there are many similar tokens, then we send it to the read mapper and do the actual check. And if not, then we can discard the location. How would I map these two operations to SISA? Well, getting the bit vector can be done with a set operation. We just take the bin and extract the set of all tokens it contains. And we store them as a sparse array of tokens. To receive the bit vector that is associated with the bin, we just take the union of the sparse array with a bit vector of all zeros. And SISA control unit would map this operation to processing near memory as sparse array is involved. Then comparing the read sequence to the bit vector would be done as follows. Firstly, you would create a bit vector for the read sequence in the same way as you do it for the bin. Then you've got two bit vectors, and you need to compute the intersection. Well, and SISA would map that to processing using memory as two bit vectors are involved. So this is how, in my opinion, it maybe could be done. Some similarities and differences with graph mining. Similarities. The computation is bottlenecked by memory. We can introduce that notion to reformulate the algorithm. We can leverage SISA's high-performance set operations, and we can use both processing using memory and processing near memory, and let the SISA control unit automatically schedule to tackle the memory bottleneck. But there are also some striking differences, and maybe the example is not perfect, but as said, I've spent quite some time searching. The difference is that GRIM filter does not have a complex algorithm structure. So the set notion doesn't release any parallelism because there's nothing that is hidden. The parallelism in this algorithm is pretty obvious. And of course, it's the possible acceleration of one application rather than a whole problem class. However, this is how a problem could be mapped to SISA that is not graph mining. And maybe you can think of other problems. And the last discussion point is that I already said that I wanted to introduce some controversy. And I said it's a promising cross-layer design. And I also said it's innovative rather than explorative. Question is, how would you rate the novelty of SISA? And in general, how novel is the composition of old results to form a new solution? Yes and no, I'm happy to either take further questions or discuss about the points.
Yes, I specifically, I had a question about something you mentioned about how they used processing using memory and processing near memory in conjunction. And I was wondering, you kept saying, you mentioned a lot of times that that's assuming that they're both sort of available as building blocks, but how, I mean, more specifically, did the paper mention how they sort of imagine going about having this? Because how would you, is there like part of the memory that specifically has these processing using memory capabilities, and another part that's the 3D stacked memory, or is it like they're both merged together and they're like certain parts? Because if they're separate, how would you handle mapping like the data to the right place?
No, you can actually combine them. Then the reason is that Ambit uses those specific rows to do the computation. So if you look from outside, the Ambit doesn't change anything about the DRAM interface. So you can actually combine both of them.
Okay, so you'd have sort of this like 3D stack memory.
Yes.
With where the
With
memory part
processing
has
in-memory
processing
elements.
Okay.
Yes.
So in that case, why would you have to sort of separate the two in the way you're thinking? Like, because you said that sort of SISA uses either one or the other, but can't you sort of find a way to?
Well, the reason is that as soon as a sparse array is involved, you cannot, nowadays you cannot compute it using memory, because, for example, Ambit just works for those bitwise operations.
Okay.
And I think at the moment, all other architectures that have processing using memory, they do not support instructions for those sparse arrays where you don't do bitwise computation.
Okay, so maybe just kind of how did they mention specifically how they represent these sparse arrays? Maybe you mentioned them in the presentation. I missed.
Well, you store the integers.
So just
like you would do it
yes.
normally in memory. You just store the integer values that are in the set.
Okay, so how would you differentiate the sparse array from the dense array?
You have for each set you have some metadata associated with it, and then the SISA control unit uses this metadata to choose how to execute it.
Mm-hmm. Okay, but imagine, so what if you had two sparse arrays that represented sort of data from the same indices? Wouldn't those be able to be computed as like bulk bitwise operations? So if you have two sparse arrays that are kind of sparse in the same way,
mm-hmm.
in that case, like,
but
maybe
what set operation would you like to do on them? Because if you do, then you get the set again. If you do the intersection, you get the set again.
Okay, yeah, I see what you mean. Yeah.
So I don't see how this could be useful.
Right, yeah, okay. Yeah, no, I see what you mean. Thanks.
So I have a question and a comment. My question is, but it's probably more of a question to the authors of the paper, but this idea seems very useful for industries. For example, like Google or Facebook, they could probably do a lot with these this graph mining optimizations. So has there been any comment or work that has happened with industry because of this paper?
Well, the paper is pretty new. I think it's from 2021. It's on the first slide, but I think it's from 2021. So I don't know if any cooperation with industry happened yet. In the paper, it doesn't mention it.
Okay, all right. And then one more comment about the novelty.
Yes.
Maybe I would say that composing all the results does not have an effect on the novelty of a solution, because like a comparison I'd like to make, for example, is sometime in the 70s, there was this operating system called Multics, and most modern operating system solutions are heavily influenced by or even reuse solutions that was used in Multics, even though Multics wasn't a conventionally successful operating system, but it still almost influenced every single operating system since then. But even though we wouldn't really call these new operating systems not novel, they may have reused or been influenced from Multics, but that even though the fact that these operating systems had to identify and reuse these ideas and combine them in a non-trivial way would still suggest novelty and would not make their solution any less novel than creating something new entirely, I would say.
Well, in fact, I agree with you. I just wanted to put it on the weakness side to be a little controversial here.
Yeah, I understand.
I also thought about the question, how novel is composition of old results? And I thought when we look at processing in memory, using innovation instead of doing something completely new seems like a good thing, right? Because you talked about how it's good to have or use the existing infrastructure. So actually it's an advantage to not need something new, right? Because it sounds so negative when you say innovation instead of exploration, but I thought sometimes this could be good.
Yeah, I think so too. And actually, one of the strengths, if you remember, was that very few really special purpose hardware is necessary. So yes, I think indeed that's a nice thing, that not everything is completely new and special to the graph mining problems.
Right.
So just to follow up to what you just said, do you not consider processing near memory as special purpose? Because like TestRack, for example, if I remember correctly, is like specific for graph processing and stuff like that. So
when I say assuming that they do exist and are existing building blocks, I'm looking a little bit into the future,
right,
because we need to tackle the memory bottleneck. It seems like those concepts are pretty promising.
Mm-hmm.
So yeah, it could be that they get building blocks, but of course it's not sure.
Okay, so yeah.
At the moment, yes. At the moment, it's special purpose hardware.
So you're mostly looking at like, how is SISA like I guess a good application, given that we have all this stuff, like a good way to.
Yes, exactly. And like, I mean, what I mean is processing near memory and processing using memory is not special to a specific problem.
Mm-hmm.
And yeah, and if it actually comes that way, then there are building blocks that are just available.
Okay. Right.
So I think my question is a little bit less interesting than the discussion that's going on, but sorry about that. But you mentioned, well, maybe not, you mentioned that set notation reveals hidden parallelism.
Yes.
I'm not quite sure how. Could you maybe explain that again? I didn't quite catch on that. What exactly is meant by this point?
If at the beginning you have those algorithms, it's pretty hard to detect parallelism. And if you reformulate them, which takes some creativity, then all of a sudden you have those set notions. And the operations on the sets at many points can be done in parallel. And apart from that, the set operations themselves provide some parallelism. So that's how you reveal some of the parallelism.
Okay, I see. Yeah, these bitwise operations are highly parallel.
Yeah, exactly.
So in general, it is a difficulty parallelizing graph algorithms or not? I'm asking as a complete noob here.
Well, the paper does it for many algorithms, so I suppose it's possible. But of course, you need to analyze the data structures within the algorithm and reformulate them using the sets. So it's not straightforward, I would say.
Okay, thanks.
Is there anything on YouTube? Okay, then if there are no further questions, I thank you a lot for listening. And yeah, big thank you also to my mentors, which helped me a lot. And I guess that's it then.
Okay, great. I'll make a few comments quickly, I think. Yeah, thanks for the presentations. I think this was a very good discussion and very good summary of the works. Clearly, the second work is, as you said, an algorithm across the stack CoDesign. I'll mention the novelty point a bit. I certainly think the cross-layer design on an important problem is novel, even though individual components may not be novel. But I think there's an individual component that's also novel in this work, which is really the set-centric ISA concept. I haven't seen any proposal in the past that has really thought about instruction set architecture in a set-centric manner. So the instructions that are added are, in my opinion, are novel individually if you take out everything else in the paper. Basically, that will stand still as something new, I would say. And I totally agree that I think the paper does not really do a good job on emphasizing how much more applicable this concept and the design is, right? Because certainly sets are much broader than graphs, and there are many bit vectors are representable as sets, right? As you mentioned with the Grim filter, and I like your example quite a bit actually. Maybe it's good to look into Grim filter implemented on something like SISA, which could make the performance of Grim filter much better also, because that's one of the issues with the Grim filter as it's implemented currently. The performance and energy benefits are not as high as I think they could be, really. So certainly there are other applications that the paper doesn't cover. Hopefully future work will figure out that there are other applications that can benefit from it significantly.
Yes.
Yeah, and I think the last point, the paper is so recent that we'll see if there is any industry interaction and uptake. Industry is still, as you have seen in the lectures, industry is still always slower than the research, right? They're just adopting. Alibaba, you mentioned, I think in the earlier talk, there are 4 major companies that are now actually implemented processing in memory chips that are serious, I should say. Some people are experimenting with, like emerging technologies. I don't include them, but 4 major companies have implement these chips, and they're not there yet in processing using memory, for example. That's not something anybody implements. So over time, I think people will hopefully adopt this sort of ideas as well. Yeah. That's all I have.
Yes. Yeah, I've got nothing more to. Then have a nice evening, everyone.
Great. Thanks.